Dear Professor and everybody, I'm Ms. Xuan1 from working at University. It's nice to meet you. Today I want to present my research is selective resolution of chiral isomer of diastereomeric acid by diastereomeric crystallization. First of all, I'd like to talk about enantiomers. And you know, enantiomers are diastereoisomers that non-reversible mirror image. You can see here. You can see here. This molecule is the mirror image of the other molecule. And the diastereomer are the stereoisomer of a non-reversible but they're not mirror image. You can see here. 1, 2, dimethyl propan, cyclopropan. In the solid phase, two enantiomer makes the racemic solution in the 50-50 ratio. And there, in the solid phase, there are two chiral compounds depending on the molecular structure arrangement. You can see here. For the conglomerates, for each crystal, they have the one chiral configuration for L or D and the mixed mechanical each other. But for racemic compound, for the unit cell, they consist of two chiral enantiomers, D, L, but with the fixed order, for example, LD, LD, LD. And the last case, solid solution, it have in the unit cell, they have two chiral enantiomer. However, they have different pattern or order. You can see here LD, DD, ML, or DL or something here like this. And nowadays, there's many people try to separate the chiral compound, but because they show that some enantiomers have the different biological activity. Sometimes some enantiomers have toxicity, but the other enantiomers are non-toxic. So, especially in pharmaceutical field, enantiomer drugs are developed to instead of racemic drug because they have the more effective biological activity. And the last reason is so important is they want to know the mechanism, molecular mechanism, recognition of the body system, such as the molecular recognition between enzyme and substrates, or receptor and or antigen and antibody. You can see here. To obtain enantiomer, there's three chiral approach: is chiral pool, asymmetric synthesis, or racemic resolution. However, racemic resolution is always the widely used first, almost synthesized substance is racemic resolution. And they're very easy to control the experiment condition, and they have effective economy. For racemic starting material, we have three chiral methods. There is kinetic resolution, diastereomeric zone formation, or referential crystallization. Unfortunately, referential crystallization only apply for conglomerates. And kinetic resolution is very difficult to control the material, to control the condition. So diastereomeric transformation is the most widely used. And its advantage is high yield because sometimes they can obtain 100% and high applicability because this method, the principle of this method, is shown in this slide. Here. In solution, here is racemic compound. Some additive will interact with isomer and forming diastereomeric stones. 1, 2, for example, L and additive or D and additive, because they have different physical or chemical properties, so you can very easy to separate the enantiomer by using conventional separation methods such as distillation or extraction or something. And however, resolution efficiency can be affected by resulting agent stability different up to diastereomeric stones and some operation condition, for example, separation, pH, agitation, steeping, or temperature, and so on. For my research, I'm using mandelic acid as the starting material because enantiomer of mandelic acid is useful for chiral separation of amino, alcohol, and alcohol. And the second reason is enantiomer of mandelic acid is useful precursor for synthesis from antibiotics such as penicillin or cephalosporin, and they can use for anti-bacterial agent. However, in my knowledge, I think the separation of racemic acid to chiral isomers, they have a low applicability or low efficiency. So we try to investigate try to find some resulting agent for chiral separation of mandelic acid with high resolution efficiency. And the second purpose is I want to investigate effect of ratio of mandelic acid to resulting agent from the chiral compound, and then suggest some molecular structure to separation chiral compound. First experiment is schedule. First step is choose resulting agent. Second is effect of mandelic acid concentration and some operation conditions. And my experiment can be used Russian reactor by doing crystallization. And temperature of that can be controlled by Chiral brand 180 and using software Selective to control the temperature of fire. And there is some result and conclusion. From 25 different compounds for resulting agent, I choose L-phenylalanine is the resulting agent. And enantiomeric axis is 50% for the beginning results, 50%. And resulting agent, resolution efficiency is 56% for the starting tool. Here is mechanism of chiral resolution of mandelic acid with L-phenylalanine, because L-phenylalanine have carboxyl group and amino group, but the mandelic acid have carboxyl group and OH group. So in solution, in solid phase, it made diastereomeric by forming some hydrogen bond like this. And here is a molecular structure of diastereomeric stones was published by Professor Ishimura in Analytical Science journal. For the diastereomeric acid L-phenylalanine diastereomer, we have 6 hydrogen bonds. Yes, 1, 2, 3, 4, 1, 2, 3, 4, 5, and 6. However, for this at this point, there's bifurcated hydrogen bonding. So for the diastereomeric acid L-phenylalanine, the molecular backing I think is more loose than L-mandelic acid L-phenylalanine. So L-mandelic acid L-phenylalanine have lower solubility in solution, so they will crystallize out in chiral resolution. And the different molecular structure of D and L diastereomer is shown here is Z-axis length and beta angle, as you can see here. Because resulting agent concentration is so important for chiral resolution. So for the first experiment, I tried to change the concentration of resulting agent is what you can see here. At this point, from the sample, the ratio 1, 0.7, 0.4, you can see here, the chiral resolution or optical ability is no change. It's no change in here. However, the ratio of mandelic acid and L-phenylalanine obtained crystal a little change at the sample 7.7 and 1. The ratio is 1:1. However, for this sample, the ratio is not different because I think yes, you can see here the mandelic L-phenylalanine is 2 times as much as mandelic acid. And I tried to maybe from here we think they form a different molecular structure. So they're using XRD to investigate molecular structure. You can see here. As this peak is the 22, and this peak is 28 degrees. Is the characteristic of the mandelic acid L-phenylalanine. Whereas for this peak and this peak is characteristic of L-phenylalanine and L-mandelic acid. The XRD spectra of the sample is 0.7 and 1 sample. Sample 1 we have XRD spectra similar to mandelic acid L-phenylalanine. However, at the sample 0.48, we can see here they have characteristic of L-phenylalanine, L-mandelic acid, but they also have the characteristic peak of L-phenylalanine here and here. So I suggest that in this case, L-mandelic L-phenylalanine will co-crystallization with diastereomeric formation. And the second experiment, I tried to increase concentration of mandelic acid in solution, and they show that when the ratio of mandelic acid L-phenylalanine increased from 1 to 6, the opticability increased slightly. However, at this ratio, the opticability decreased suddenly in the senior. And they show the from 1 to 6 ratio. The ratio of magnetic acid and alphenylalanine is 1:1. This means they have. This means the diastereomeric is also the 1:1 complex. However, from this ratio is different. So I'm using DST method to determine the melting point, because impurity can be reduce the melting point of diastereomeric combination. Fonts you can see here. And from the step, for example, from 1 to 6, we have the XRD peak similar to alphenylalanine. Alphenylalanine, they didn't show any characteristic of the magnetic acid alphenylalanine. So we strongly suggest that maybe because the magnetic acid alphenylalanine and L-Mandelic acid alphenylalanine, they have a similar molecular structure. So the magnetic acid integrates the lattice of L-Mandelic acid, the L-phenylalanine, yes, from this case. But at the ratio 7, and we have the different XRD peak from here. Yeah, you can see here. It's the combination. It's a combination of L-Mandelic acid, L-phenylalanine, and DL-Mandelic acid. So, and this result can be confirmed by using DST machine to measure the melting point. You can see here. And this peak is very close to melting point of DL-Mandelic acid, and this peak is similar to melting point of diastereomeric LL. However, it's a little shift because of L-Mandelic acid effects on the diastereomeric melting point. From the results, we conclude that alphenylalanine is useful resulting agent separation chiral isomer magnetic acid, and the final result is magnetic acid can be enriched to around 90%, and diastereomeric sum of magnetic acid and phenylalanine is away from the 1:1 complex, regardless with the ratio of magnetic acid resulting agent. And the magnetic acid acts as the impurity to integrate the lattice of L-magnetic acid, L-phenylalanine.